speaker is Dr. Gunther Witzel. He will talk about the recent result from observation on Sagittarius A+ variability with the Spitzer, BLT, and Keck telescopes. The introduction of Gunther will be made by Rainer, so I will give you the micro, please.
Yeah, good morning. So it's a real pleasure to have Gunther here. He's been visiting all week. He's still here all day today. I know him from University of Cologne, where he came to do his diploma thesis just about when I was about to leave to come here. And he graduated there with his PhD in 2012, working on a problem mostly of polarization measurements in the near infrared. And then he went on to UCLA, to the Galactic Center group of Andrea Ghez, and now he's back. He has a position now at the Max Planck Institute for Radio Astronomy in Bonn. And I expect him to have in a year his own group. And and he's a real expert on the Galactic Center. He knows radio and infrared astronomy, and he's the kind of person you call when you have a complicated problem and you want somebody really sit down and drill down into the very details of it. So he did that with polarization. So he's like, if you want to build an instrument at the Nasmyth platform that measures polarization, call him. He can tell you exactly what you have to do and how you calibrate that. And also now you will see he has done the same thing with his light curve measurements. He's now an expert for a specialized case of Sag A star, but I guess it's more generalizable. Also a time curve analysis, and I think what he presents a bit, he kind of kills off the last 10 years of research on that. It wraps it up basically. So thank you very much. Here's Gunther.
Yeah, thank you very much, Rainer, for the nice introduction. I would like to thank you, first of all, for inviting me to give the seminar talk. It's a great pleasure for me to be back in Europe, and simply to be able to travel now here. The invitation stood already for quite a time, and now finally I can make it to Granada. Yeah, Rainer was actually the one who introduced me to reduction methods, especially for time series analysis on the black hole of the Galactic Center. And so if he tells everybody that I'm drilling down so deeply in everything, you know, I have learned it somewhere. And, you know, this small overlap we had in Cologne, that was certainly very important for me to get really started with my research in my science career. So what I would like to talk about today is data, infrared data from the black hole at the Galactic Center. These are time series that have been basically taken from the moment where adaptive optics came on. So we're looking at a large data set that is in large parts historic. We have complemented this data set now with Spitzer data. I will tell you exactly why that is such a breakthrough. And normally I'm used to, as Rainer also just did, look a little bit retrospect at what has been done before and what we can say now, and show you how we are a little bit more definitive in what we can say. But actually now, because the Galactic Center is such a dynamic research field, gravity came on. And suddenly there are a few things about the variability of Sag A star that become very clear. And I actually think that these definitive answers that I hope I can convince you today that we found for the variability will be actually one of the puzzle pieces that will really allow us to understand what is going on in the accretion process around Sag A star. So I'm actually really thrilled. The gravity results came shortly after we published this paper, and it now becomes really interesting again. So yeah, so it should be a little bit more towards the future now, the talk, than to the past. Yeah, I will talk about gravity in a second, a little bit more. First of all, this is a collaboration, of course. My colleagues at UCLA were very much involved, and I would like to point out Greg Martinez, who did a lot of the coding work and is the statistics specialist that I could rely on. Then, of course, for the Spitzer part, we have the group of Giovanni Fazio, Stephen Billner, and Joe Hora, very important for this project. We had support of Charles Gammy for the theoretical aspects of the paper, and there is of course a larger group of people who are involved in writing proposals for Spitzer and also in the multi-wavelength campaigns related to the new Spitzer data. Okay, Just to give you a short introduction, what it is when we talk about radiation from such a star and the variability. This is a map of the galactic center of the, you see this are about 8 arc seconds or 1 light year. You see here the mini spiral very prominently in the radio at 1.3 centimeters. And you see here a very bright compact source in this image, and this is such a star. This source is very, very bright, but in the radio a rather steady source. It was soon, or very soon, or after taking the first images that allowed to detect this compact source, it was assumed that this is related to a black hole, but of course nowadays we have much more evidence for this because of the fact that in the infrared we see stars orbiting the black hole. So we know much more about the actual nature of this source. For a long time in the infrared it was not possible to detect the source there, but with the onset of adaptive optics you could, and this is now an image taken with the VLT, and it's an HK L-band composite, and it shows you this inner region. Again, you see also in L-band the mini spiral, and then especially here this region, which is the region of all those S stars that are orbiting the black hole, and are object of the dynamic studies now in the latest developments to show effects of general relativity. At this position here, and where you basically don't see anything, that's the position of the black hole. So in the infrared, the situation is a little different than in the radio. You most of the time don't see a source at this position, or barely. But at times, this is very different. So you can sit at the telescope and it would become much, much brighter, and you will suddenly see a point source at the position of the black hole. So very early on there was much interest about this extreme variability in the infrared, and people tried to understand exactly how this is generated, how does this relate to the accretion process, or what is actually behind this variability. Is it, for example, a jet? Is it the accretion disk itself? And what are the properties of this accretion? Now, such a star is a very special beast. It is not your typical AGN. It is a highly underluminous black hole, and there was an own class of models that have to be developed, inefficient, radiatively inefficient accretion models that have to be developed to understand actually why this black hole is so dim. I show you here an SED, and this is a compilation of much data, and this is more or less a classical picture that has been developed before. And what you see is here the radio develops into this kind of sub-millimeter bump. There's a sub-millimeter axis. And then you go into a range where you actually don't have many measurements. Right? The extinction towards the galactic center is so high that you will not be able to, for example, observe it in the optical. So you need to piece together a more or less incomplete picture. So what I would like to point out to you is that here in the infrared especially, you see mainly upper limits. And that is due to the fact that often you don't see the black hole, but if it's there, you see it variable, and so it's very hard to understand which part of the infrared radiation might relate to the more steady radio. And then again, you have a large gap, and you have extreme X-ray variability as well that has been observed. Now, how was it interpreted? This more classical picture of Yuan et al. Says that, well, you have two electron distributions that are needed to really understand this. One is an electron energy distribution that is thermal and that creates synchrotron radiation, which can explain this bump. And then you have a wider distribution of non-thermal electrons, accelerated electrons, that can explain the longer wavelength part, and then potentially makes predictions for the quiescent state in the infrared. Now, it is pretty clear from the observational facts that we look at optically thin synchrotron radiation in the infrared. So it is, first of all, variability that happens at very short timescales, and secondly, it's polarized. And the spectral index that you can observe, at least at brighter states of the black hole, is in the order of minus 0.6 or 0.7, so a canonical value for optically thin synchrotron radiation. So just to show you a little bit more about the phenomenology here, I show here a video or a small movie that Reinhard did. It's from observations in 2007. And please follow here the time. So you see how the source can become much, much brighter in something like 10 minutes. So over a night, when you sit there, you can really follow this, and it's a great excitement. And I think everybody who observed the galactic center in the infrared experienced this, and it's a kind of a hazing ritual for new students to observe the galactic center and the variability. And this is how it looks like if people see it for the first time themselves. So this is Anna Churlo, who is a postdoc at UCLA, and Devin Chu, who is a student there, and they helped me with some monitoring campaign, and so it popped up in H-band in this case, and the excitement was big. Now, I said before, one has basically only this very indirect tool to look at light curves and to learn about the spectral properties of the source, the timing properties, and from there you try to extrapolate, in some sense, what could really be the cause of this variability. However, not long ago now, there was a major progress published now in 2018. It's a couple of weeks ago now. The gravity collaboration showed actual evidence for an accretion disk and for a hotspot moving in the accretion disk. So gravity is an interferometer that combines the light of all 4 8-meter telescopes. It's an interferometer in the optical or in the infrared that provides a maximum baseline of about 130 meters. So it's a major achievement that now interferometry is possible in the optical. And the gravity collaboration actually measured a sequence of astrometric points that between such a star and SO2, the star that came closest, now had closest approach just in 2018. This is basically, it's so close that it's in the same beam, and it gives you the interferometric signal of a binary. And so you can have very precise distance measurements. And it was mainly used, or first of all used, to track SO2 and understand the gravitational redshift that now happened during periaps of SO2. On the other side, of course, on shorter time scales, you can use SO2 as a reference and look what happens with the position of the variable source, such a star, during a flare. And that's what they did here, actually at multiple occasions. And one result that you can see here is that in XY, indeed, the astrometry of the origin of the flare is a circle around the average position. And in another flare where they could actually take a full linear polarization Stokes parameters, you can show that also you have a rotation in the U and V plane. And this rotation is exactly one loop during one physical rotation in the sky. And that has been now taken as evidence for tracking a hotspot in an accretion disk around the black hole that is rather face-on in the sky. So this is, of course, really exciting for me after years looking at the variability light curves, that there might be now really a way to look at the process in this close way. However, when these are preliminary results, I think these experiments have to be redone and be more refined. This is a very, very important piece of the puzzle, and I still think that we can learn really a lot from the light curves themselves, especially when it comes to the radiation processes. And so I would like to show you now in detail what our experiment was in this context. First of all, a view of the historic data. So this is the NIR variability of such a star as we have seen it with the VLT and KEK in red, black the VLT. So this is time, this is flux density. It is here presented dereddened. And I have removed all the gaps from the data. So this is, of course, something you should not do for time series analysis, but you can do to demonstrate basically the phenomenon in one plot. Oops, sorry. And So what you can see here is that this light curve has an well-defined baseline, and then these asymmetric peaks that go off of this baseline in a typical time distance, if you want so, which is not periodic. So the flux density distribution is very skewed. We have a well-defined average of this light curve, which is a very important point. So interestingly, if you look at other sources, for example, AGN light curves, since the involved timescales are so much longer, often the time series analysis suffers from the fact that you don't know the true average of the process. And I think it's kind of a trivial statement, but it's still important that you can only do proper time series analysis and really understand statistically what's happening if you at least know the mean of your process. So this is a comment I'd like to make. So we are in a very lucky situation, actually, that such a star is most of the time so close to the detection limit, and then on top of it has timescales that allow really to see this average with enough precision relative to the maximum outburst to really understand what's going on. Now these are 20 seconds, 20,000 minutes about, so we're talking about a very low time coverage of those 10 years that this data covers. But this was a picture we had from the ground-based data. Just to give you now a small summary of what has been, based on this data, the facts that have been agreed on in the literature. Yeah. The first one is that this is a stochastic process. And I think nobody doubted that, even at times where people were more interested in looking in deterministic aspects of the light curve. There was the claim of quasi-periodicity and so on. That you cannot really predict when such a star is going to flare. So it is indeed a stochastic process, and the power spectrum can be described as a red noise process. The flux densities, as I've shown you, are so asymmetric and very skewed. So it can be described by a power law or a log normal distribution. This was also disputed a little bit, but it's very hard actually to make this differentiation in the presence of white noise at the lowest flux densities. It is a continuous process, and it has a characteristic timescale of a few hours. That's what you saw, that basically this process was reverting to the average in a more or less regular way, well within our observing windows. There is no indication of something more deterministic. That doesn't mean that it's not in there. It is just not possible to really show that significantly with the existing data. And if you look into multi-wavelength campaigns, and you will see that you can find correlations between the X-ray flares and the submillimeter. And how these correlations are, I will show you in a minute. They are a little bit complex as well. What I mentioned before, we have the radiation is linearly polarized, which is a strong indication for synchrotron radiation. And you can measure the spectral index in the NIR, and while it is at brighter states very typical for synchrotron radiation, it seems to vary in time and possibly also with flux density. And that, of course, is a strong constraint on the radiative processes. So what were the open questions? The open questions were, can we actually determine this correlation timescale more precisely? That is something that is also done for AGN studies, and where people believe that you might actually find correlations between black hole mass and the variability timescales, or that it is at least a tracer of fundamental properties of your accretion process. Now, I would always argue that this timescale of a variability process is indeed an observable of a black hole accretion system. And so it makes sense to, if you can measure this observable, to actually put some effort into it to make it a precise number. The other question is, can we determine the flux density distributions properly? So just to point out what I mean with flux density distribution. The flux density distribution is the histogram of occurrence of flux densities. So it's not flux density against observing frequency or something. It's not about the spectrum, but simply about which fluxes occur how often. If you can do this, you might actually infer spectral properties from this, if you can do that for multiple wavelengths. Is there an indication of multiple states in the light curve? So is this all a homogeneous process, or do we see it sometimes in very extraordinary situations, and what would be the differences? How does the the PSD look like at shortest time scale? So the power spectrum, as I said before, is a red noise power spectrum, but there were ideas, especially from theoretical side, that you would expect a loss of power in your power spectrum close somewhere to the innermost stable orbit frequency of the black hole. So the question is there a signature in your light curve of orbiting matter at the innermost stable orbit? And what is the NIR spectral index? Does it change indeed, for example, with flux density, and what can we actually learn about the radiative processes from this? These were the questions that could not really be answered before. Just to give you a little bit more illustration of some aspects that I just said, first of all, the flux density distribution, that is very skewed. So that's what I just said before. You have here on the x-axis flux density and simply frequency of occurrence. And these are the fluxes in K-band that have been measured. And you can describe this, for example, with a power law distribution. This turnover here is caused by the intrinsic, but not by the intrinsic, by the measurement noise. But the intrinsic part of this distribution can be described by a power law. And here you see basically two limitations of the data. One is here, the white noise of your measurement, and on the other side, here the highest fluxes are underrepresented with respect to the power law, which is the effect of the intrinsic correlation. And so the correlation in a red noise process, the flux densities don't occur independently, but you have flares that actually build up to a certain flux density and come back. And that means a bright state always comes with a tail of low and intermediate states. And this kind of correlation actually for the highest states can lead to under or over representation in the histogram. And then on the other side, we detected a so-called flux RMS relation. So one of the most or important characteristics of this variability is that if the source becomes brighter, it becomes more variable. So if you want a large step from one point in time to the other, then you should be already at a bright state and not at a dim state. And this is considered by the X-ray binary community as a more fundamental property of the variability than the power spectrum because it stays constant